nanohub.org.
Online simulation, and more for nanotechnology.
It's really nice to be here. Several times I've been to the Burke Center, and it's a marvelous place, and the Discovery Park, and Purdue is obviously a great engineering school and a great university. I sort of have spent most of my career at Bell Labs and Sandia Labs, and then at Santa Barbara and Harvard, where I've been dean for almost 20 years, more than enough time to have caused enough mischief, I guess. But I have been, in the last 10 years, been more on a philosophical view. The role of science and technology in the brighter world and its relationship to society and education. I went to Harvard not because, in fact, there was no engineering school, and Santa Barbara had a great engineering school. In fact, in my field, Santa Barbara was much better in materials and electronic materials and devices. But their students were obviously very good, undergraduates, and had had liberal education. And I always felt that engineering is a lot about the future, about building something which is and it must relate to society. In fact, engineering in many ways, in my view, was a liberal art. It was because you not only need to know mathematics and physics and chemical engineering and all those other fields, but you also relate to society, and we must actually educate our engineers differently. So that's been my mission in life. Second, I started teaching public policy at the Kennedy School after I stepped down as dean, because I wanted to actually teach undergraduates technology and society. And so, in fact, that's what I was doing. And then John Holden went as president's science advisor to Washington, and the Kennedy School dean calls me and said, will you head the science, technology, and public policy program? Actually, it was started by my predecessor, Harvey Brooks, the well-known, who was dean of engineering and applied physics at Harvard. And it fit with what I wanted to do. So I started teaching master's students in public policy. And then I would teach, one of the first lectures would be what Vannevar Bush said, science, the endless frontier. And I had this student of mine, postdoc, who was my teaching assistant. And I don't know how many of you have read Bush's paper, Science Day. It is absolutely beautifully written. It is absolutely, it makes you get goosebumps because it's so well written. And at the same time, I grew up in Bell Labs. It was the place where transistors were invented. It was the place where information theory was invented. It was the place where CCDs were invented, and you can name it. And I asked my student, would you find out how many times Bush refers to science in this manuscript, and how many times does it refer to engineering? Science was referred to 130 times, and engineering 4 times. And Bush had been dean of engineering at MIT, no small school, and he had been a PhD of Harvard. So I said, there's something wrong. And I said, what are the examples he cites? He cites, of course, the atom bomb. And of course, you can say because of E equal to mc squared and fission, that belongs more to physics, even though obviously engineering and chemical engineering were very important. But then the others were proximity fuse. When I think of proximity fuse, I think of electrical engineering. And then he had radar. Again, I thought of electrical engineering and applied physics and all the, and then he had synthetic rubber. I think of chemical engineering. All of that got confused as science. And it bothered me because at Bell Labs, and then he also said, national science should support basic research. That's why it is science is the future, science is the endless frontier. This is not against science. I'm a physicist and low temperature physicist, but rather a much more holistic view, because he separated basic and applied research. Bell Labs, we never use the word applied research. Go look at NSF. Every one of its directorates, they don't use the word applied research, but it got codified in the rest of the federal government. Because research is about the unknown, something new, something different, something which you don't understand. It has nothing to do with the basic or applied. There will be things in technology and engineering which you don't understand and we knew, and the same will be true for science. So the whole notion of applied research was a mistaken notion. And in fact, Bell Labs managers knew that. So I had this student, because I now had the time. I also had an undergraduate student in physics. I said, will you go look at all the old literature of Bell Labs? And what did the vice presidents and all say about research? So I dug up, and you should know, His name is Ralph Bowen. He's referred to a lot in my book, B-O-W-N. He's an IEEE Medal of Honor winner. He was the director of research when the transistor was invented. And you know the transistor's famous people, John Bardeen, whose undergraduate degree was in electrical engineering. His PhD was in physics. You should know he was both an electrical engineer and a theoretical physicist. Bratton, who was really an experimentalist, a materials person, and Shockley. And Bardeen took the data with Bratton when the transistor was invented. And they not only did not want to call the director of research until they actually had seen that this thing amplified something. So they know they had something. That's what I learned physics that way. We tend to forget that you actually make sure it's observed. And then the director of research was Ralph Bowen, and he then started giving a lot of talks. And he gave a famous talk to George, which I dug up from the literature. It is in the Bell Labs library. It's not in a peer-reviewed journal. It is the most beautifully written paper about the nature of research. Right up front, he says, we don't separate basic and applied. And that is a very important change in the construct. Because the bias was Harvard didn't have engineering. Oh, that's done at MIT, as if MIT is not a good institution. MIT is one of the greatest institutions on earth. Bell Labs was one of the greatest institutions on earth. But completely the arrogance of physics, or some fact, I'm saying it as a physicist, you should know, it really has bothered me ever since. So since the last 10 years, I've had one mantra: we're going to change that conversation. And engineering and science have to be brought together in a truly holistic way. So you can stop reading and say, this is the book. And that's why there is a new name. So I started reading all the literature. Then, Thomas Kuhn wrote the famous book, Nature of Scientific Revolutions. It's all the great theoretical physics, from special relativity to quantum mechanics. Of course, they're great things. But that's only part of the story. There is a missing feature, what we say in the vocabulary, technoscientific, because every advance in science ultimately has been observed through some variation of technology. Technology and science are so intimately linked together that, in fact, real thing you should talk about is the technoscientific revolution. So, in fact, this is true. If you look at Fermi, was actually one of the greatest physicists. He actually developed the nuclear reactor, the pile, and all these other things. And you can say, no, only E equal to mc squared was important. You would never have gotten anywhere without the rest of that verification. So they are intertwined. Sometimes the science is the leading thing. Sometimes it's the technology. Sometimes it's both simultaneously. And in fact, the transistor is a wonderful example. That's also true for lasers, it's true for information technology, etc. And they never asked, is this basic or applied? It's like caste system, where now in the modern world, there should be no caste system. Even in India, it's outlawed, even though people still practice it. So there is no caste system. There is a great deal of creativity in all the different disciplines, and we must begin to appreciate that, and so on. In fact, I found after the last 10 years that engineering and technology are in many ways much closer to biology, because nature evolved things in this way. You cannot solve it from reductionist thinking. Not that reductionist thinking is bad, but reductionist thinking is only a piece of it. You've got to understand how things actually evolve as a function of time. In fact, that's how I convinced Larry Summers that Harvard needed an engineering school, because in fact, that is the future of life sciences, because life sciences and engineering are much more closer together. Engineers build artificial networks. Biological networks, of course, happened through million years of evolution. And so you really have to, so I've spent a lot of time understanding the language of the biologist, not just the language of the physicist, my own field. And so I really think that is basically, I don't need to say any more. That's what you have to read in the book. So we need a new discourse, and discovery research is not just going to happen from science, it's going to happen from the union of science and technology. It almost always happens that way. So that's why we wrote the book. And I want to, right at the very beginning, mention that I had a whole lot of people. This book has been 4 years in the making, and I had lots of people review it, from chemical engineers to theoretical physicists to computer scientists. and social scientists, because I want to appeal to this larger audience and still make sure all the physicists and the engineers didn't throw me into the bus, under the bus. So I don't know yet. They may yet throw me under the bus, but I think there is some meat there. I have a lot of good people in there. And then Harvard University Press has its own set of reviewers. We had 2 excellent reviewers. They went through line by line. I'm really, in that sense, I'll give Harvard credit. Their press is quite a good press, because I've written books with other presses. They just want to make money. They actually want to have a quality product. And then I talked to 4 people to write more formally, and I asked John Holdren, who now is back at Harvard, because he was president's science advisor, and he's quite well known whether I'm crazy, because I am going to be giving a lot of talks to change and Nancy Andrews, who was the dean of the School of Medicine. I got to know her because I worked on a panel for the American Academy of Arts and Sciences to really bring biology and engineering together and transdisciplinary research. I see there a great future. Biology and engineering and physics and math were already together for a long time, even though people didn't quite have that understanding. And so it was very good, and she really resonates with me. And then, China is going to be the place. China is actually doing what I say. I wish my colleagues and the United States listened to it and not made prejudice, because whether you like China, whether you like the communist government or not, they realize this, and that's what they're doing. And I asked Kekan Zhui, who is the president of the Beijing Academy of Quantum Information Science, their science award winner, their Nobel laureate, who's won several other prizes, to give me, because he has asked me to review his they call me all the time. Fortunately, I never take any money, so I'm clean. So I think this is important. Yes. So I think I wanted to say all this. And of course, we have relied on a lot of past work, and not that Kuhn was bad. Kuhn was of a different time, and things have changed. Transistor is already now 70 years old. So that's so research is the front end of human society's engine powering innovation and technoscientific advance. We believe it is due for a rethink, one consistent with its nature and the need for nurturing. The second feature, all these policymakers will write policies, but they never tell you exactly how to implement and how it might be done. And it turns out the research ecosystem requires obviously great researchers, many of them sitting in this room, the young students who might be flourishing, the faculty members who are training them, but they're also who leads. Because it turns out, I've been dean of engineering a long time enough, you can get a very good dean, you can get a bad dean, and you probably know the difference. So I think it is very important for a great laboratory to have that leader who actually will not be a manager, but will nurture this kind of creative work. So I want to change that. Though I don't like the word manager, my Federico Capasso will agree with me on it. I wrote a paper, which I will show you in the end. Nobody works for me, I work for them. It's not just a cute line. It is to make the creative people succeed. So your dean's responsibility is to make sure that the faculty, they have to be mentored, they have to and if they're going wrong, they're going to be told. So all of that goes into it. It's not just a free lunch. So all of these features go, and nobody has ever written much about it. So this is somebody speaking from his heart who spent 40 years of his life actually being blessed. I said, I'm the bridesmaid. I've gone to many award functions, not because I won the awards, because the people who were there won the awards. So that's the message, that's the whole book. So if you can pay this to read, you can get the Indian edition. So I think the reason I feel at my old age, I can't be fired. I'm now an emeritus professor, and nobody can say this is the Harvard dean talking. So I'm going to speak my mind out, because I think the US institutions, I'm passionate about America. I've been here 60 years. My children, I've got 7 grandchildren, all born in the United States. And I'm worried about our country because of the way we are. We have lost our mojo. We have lost that leadership, which actually, Vannevar Bush at his time was a great leader, because politically it was correct. The physicists were in charge to say everything was physics. You can say everything is science. Of course, you can just say, or I can say everything is technology. But we know it's not quite correct. So there have been alarm signals that the US has been losing its standing with regard. Some of it is healthy. We can't be the only. There were times when Britain was the king, or Germany was the king, and we, of course, came much later. And then I was part of a panel at the American Academy of Arts and Sciences, Perils of Complacency. It was chaired by Neil Lane and Norm Augustine. And I don't know how many of you know who Neil Lane was. Neil Lane was director of the National Science Foundation and also President's Science Advisor. I've had many arguments with him because I've told him we should change some of it. But he says, Venki, you're correct, but we shouldn't do it because the politics, we have sold basic research in this fashion, and that's how we want to sell it. So it's become a political symbol. But sometimes you've got to call a spade, and the political symbol has to change. Because otherwise, that's the only reason Harvard created an engineering school. In fact, now it's come to pass. It's becoming, not because engineering itself has merged in ways with science, it's merged with biology, it's merged with society. We're talking about future manufacturing here with AI. AI is going to be huge social. You've got to understand the social and all the other complexities before AI will ever succeed. AI has got a long ways to go. The human brain, God or whoever created us, spent millennia in how it works. No computer can do it yet until they actually learn probabilistic reasoning, statistics, all the uncertainties which go with it. I am no expert, but some of you in this room are. So, the perils of complacency, Jeff Sau, my colleague, this was done with a co-author. I am best off arguing with somebody. That's another thing Bell Labs taught me. You argue, you question, and then you get there. And Jeff was a young scientist when he was vice president. Now he's a senior scientist, a man well established in his own right. He's a sort of almost in many ways father of solid state lighting. So he wanted to come and work with me. And so last 4 years, I gave him a non-stipendiary fellowship. And he started with questioning me he would come for 3 days in the month. And all day in my office, he'd be questioning me. In the end of the day, he'd produce a beautiful summary of what we had discussed. Pretty soon, after about a year of this, I was getting tired. It went from his questioning me to an intense debate about all of these things, because he'd been thinking about it from different points of view. So he's an important author. So I had him analyze what is there in the perils of complacency, data of publications. And you find that China, in total publications, has been doing very well. But if you take the top 1%, this is always, you have to know, take these with a grain of salt, but from highly cited publications, China has now overtaken the US, and the US is actually following behind even the rest of the world. So all the European countries, India, they all have been improving, and we are. So of course, some of it is good. We can't always be number one. That is going to happen. But there are warning signals there. There are warning signals in terms of how technology is coming. One of my biggest complaints is what did China, or for that matter, South Korea, do right? They started with manufacturing. They had manufacturing as a central element. And in fact, I left Bell Labs when they broke up Bell Labs. The white economists said, the manufacturing will do it elsewhere. I said, 10 years later, research will die. And that's what happened. Because you could not justify the R&D, even though we were doing such far-out work, but was related to ultimately the communications industry. And you've got to have that connection. They broke up Edison Electric, which used to be complete. I actually am very much for vertical integration. That doesn't mean they don't have to be regulated. There are a whole bunch of policy issues. The economists have ruined us in various ways. I've had many arguments with my own son. Very successful. He earns 10 times my salary because he was partner of Goldman Sachs. I said, you economists are wrong. Short term, you're doing it. Long term, we'll be killed. In fact, we lost Bell Labs because they decided, some wise people. And you look back what happened to the communications industry. MCI WorldCom, where is it today? All the other .com companies, where are they today? It ended up with 3 companies. Verizon, AT&T, Verizon and AT&T, both children of the original AT&T, and T-Mobile, which is of Deutsche Telekom. You cannot change. The communications industry evolved, and all these upstarts disappeared, despite every good wish. So think about it as you try to bake up even Facebook or Google or others very carefully and regulate them and still demand the long term. There's a whole bunch of policy issues. So I'll be writing about that. I will not be popular with many people, so you may regret having me here for a seminar. So I think there is a bill before the National Science Foundation. Finally, I think I'm beginning to be heard a little bit. The Department of Energy had Steve Chu, former Bell Labs colleague of mine, good friend. They created energy innovation hubs in ARPA-E and others. And they're not talking about called National Science and Technology Foundation. So I think there are some good things there, but I actually think it still has to be structured right. NSF is among the better places. They never talk about applied. They talk about engineering research centers. They talk about material science engineering research centers. They don't say it's basic or applied. DOE says that. If you work on photovoltaic materials, if you say renewable energy is most important for our future, if you actually make a photo cell, they say you're doing applied work, you should not be doing that. That's not basic science. I never heard that. That's not the way Bell Labs worked. That's not the way the transistor was invented by the greatest physicist of all time, John Bardeen. So this is nonsense, this division. So if there's any one message, that's the message. Then, look, if this is the core reflections of the book, it took a long time. So in my many arguments with my good friend Jeff Sau, that we tried to draw diagrams about what science is and what technology is. And finally, I said, there have been a lot of mistakes. And really, both science and technology can be thought of repositories of knowledge. This is how the technology works, this is how the sciences, but they are nouns. But really, research is about how science and technology advance. So we actually put a dot. All those of you who knew even elementary mathematics, just remember that fact. Research is about the dot. And S dot and T dot are intimately related in kind of interesting ways. And you cannot do the science without the technology, and the technology without the science. That's why the language has to be changed. It's technoscientific revolutions.
I actually thought you were talking about entropy and temperature.
Well, so in fact, you talk about entropy and temperature. If you go back to history, the steam engine came long before the laws of thermodynamics. The laws of thermodynamics were concocted to make better combustion engines and everything else. So which is the follower and which is the leader? It's like asking, and so the point is SS dot is not synonymous with research. Bush was basically wrong. He basically equated science with research. T dot is not synonymous with development. Every technology is not just developing something. He or she is doing something really new and revolutionary. Think of Edison, think of Graham Bell, think of even Steve Jobs. Even though he was not a hardcore technologist, he showed tremendous vision by integrating all kinds of complex devices with touchscreen displays and making it work. He changed the world. So that's what it is. The technology changed the world. This is especially for the young students at Purdue. Purdue is one of the biggest engineering schools. So Ali, my friend, that's your message. So that's point number one. Beyond Popper and Halpire, even my good friend Ali gave a talk in my science, technology, public policy class, talking about hypothesis testing. Hypothesis testing is only half the problem. Finding the new hypothesis is a more exciting thing. That's what Bell Labs was very good about. That's what IBM was good about in the old days. That's what General Electric was good about. That's what RCA, Xerox PARC were. They asked the right questions, which are the future. They didn't ask, is it science or engineering? So finding questions is just as important as finding answers. Constructivism is just as important, or maybe more important in my view, than reductivism. Questions and answers are networked into a seamless web of knowledge. It's a very complicated web. That's why you don't break this up in a linear reductionist fashion. Then beyond development graduation. So I want to make another point. Research, as we'll see, is about the unknown. It is about the surprise. So as you start doing some development work, you ultimately reach some kind of plateau. You can all get happy. This is your discipline, etc. Or sometimes real surprise happens. That's why it is a punctuated equilibrium. So for a long time, the technology goes in a certain fashion. And then you never know, just like the iPhone came and completely disrupted because he or she combined communications with computing and a touchscreen display, and they made it human touch sensitive, which then led to the App Store, which then led to all the other things. So you've got to really be sensitive to that kind of work. That's the future for the future manufacturing center, Ali. Okay, so punctuated requires both surprise and consolidation. And so I will never badmouth development. Development and understanding is very important, but it's a different function. There, you've got much more defined goals because you want to say, how good is that theory? How good is that experiment? But the surprise will come from the contrarians, who will say this consolidation was good up to a point, and then you will make some Newton's laws, you might get gravitation. Or Maxwell, who suddenly says electricity and magnetism are the same thing. This is really quite something. So anyway, and then beyond Bell Labs, we want guiding principles. So many people say, oh, Venki, you were fortunate that Neil Lane will tell me that, and Bell Labs is now finished. But I also learned one other thing, that lessons of history have a way of repeating themselves. And in fact, we must ask this question. And Bell Labs is just one example, but there were lots of industrial labs. DuPont, Exxon, Mobil, all of them. Why were they so creative for a period? What is it that they were doing? And they were doing both Nobel Prize-winning science as well as all kinds of wonderful engineering. And what is it which we can learn from that and do that? That's what, of course, NSF is trying by having an engineering research centers and others. Oh, we'll come back to that point. It's very important to think that, not just say it's of the past. What can we learn from the past and actually do for the future? Because what we have learned. So that's essentially the whole book, which you're going to have to read. It has got 4 chapters, and you'll have to read. The first chapter is a deeper dive into the relationship between science and technology. And then it goes into questions and answers, then it goes to punctuated equilibria, and then we go to nurturing. So we won't spend too much time, but I want to just give you some examples. I already told you Vannevar Bush was a great man, but he limited the dialogue at that time. By the way, I had my student look at all the history books, and already at that time, during World War II, Bell Labs helped National Science Foundation. There was no National Science Foundation. The Office of Scientific Research and Development, which Bush headed, had 3 main people. Bush, the president of Bell Labs, Frank Jewett, you go look at the history, and the president of Harvard, James B. Conant. They were the 3 who defined US science policy back in 1945. Frank Jewett from Bell Labs argued a lot with Bush, because in those days, the word which used to use was pure research. And so Jewett said, we never talk about research that way. So why don't we, does that mean that everything Bell Labs does is impure? So Bush called it basic research. And that became an important thing as a way of doing that, but we will know that had its limitations. So I just put that aside and so on. He recognized them, but just shoved it under the rug because he was politically making sure that this thing got funded. Actually, the correct name for the Science Foundation should have been National Research Foundation, which should have been both research for advancing both science and technology. That's the correct name for it. But I don't know. It's too hard to change the name. There's a lot, but that's still one of them. So I already said technology can also be a pacemaker. And this previous postdoc of mine, Tolu Odomos, who's now the faculty member at University of Virginia, we actually came to the conclusion that these things occurred in cycles. Sometimes it's a technological invention, which leads to a scientific discovery, and sometimes a scientific discovery leads to a new invention, and this goes on in a cyclical fashion. And partly, you'll find most of these things go in cycles, and you don't break them apart. Think about that unification. And so that was an earlier book. So what is it new we've done? First of all, we've thought much more deeply of how science, then all the other ways science research advances. Much beyond. So this is the technoscientific method in a very brief bullet. Science is about, so ultimately, the culture decides what you want to study. Even you can decide how broadly you want to define culture, but the scientific community or the engineering community also has some feeling for what is important, right? Actually, when I did the history, it was very interesting. At any given time, the culture has very different kind of prejudices. How many graduate students know how they discovered that air has weight, the atomic weight of the elements. You take it for granted. That Prince Charles ridiculed Lavoisier and Priestley for saying, these guys are crazy, they want to measure the weight of air. Of course, we all, so you know, so you can, and then when Copernicus was studying the stars, and when Galileo invented the telescope, why do you want to look at the stars? Aristotle himself declared they're immutable objects. But actually, Galileo discovered the moons of Jupiter, and then so on, lots of things happen. So the point really is, culture decides, and so in 1945, the culture was the dominance of physics because of the atom bomb. Even the atom bomb had an enormous amount of chemical engineering and all kinds of other things which went into it, but at least I'm willing to give that credit to the physicists. So the fact finding, whatever you decide, then you want to look for an explanation, and that's what the science is about. And then the biggest power comes when you generalize it. Technology has the same kind of thing. You're looking for some form. You're trying to build some kind of telescope. You're trying to build some kind of microscope. I've worked on scanning microscopes, etc. And so you want to find out which function you want to study, and then you build certain forms, and then can you actually exact it into something else? A wonderful example is the laser. When Townes invented the laser at Bell Labs, he was wanting to do spectroscopy. Means do something very narrow line width to do spectroscopy. He never imagined that it would be exacted for fiber optic communications. Or radar, how that microwave could be used for microwave ovens. So you can exact it, and that becomes very, very powerful. So in theory, in science, it's generalizing, and in engineering, it's exacting. So they're enormous. Second, the discoveries which occur in science usually happen through the engineering method. Be it the transistor, be it the laser, be it the telescope, be it the microscope, you can call it whatever, but it is clearly a tool. It's a tool. And of course, you can exact them, and then it becomes really useful. That's why the tunneling microscope, when it began to be useful for studying so many different things, really became a very powerful thing. So the engineering method and the scientific method, we label them with dots to show the dynamic behavior, and you do not separate the two. A great engineering institution must have some science in it. A great science institution must have engineering in it, and they must have a very holistic view of each other. Actually, of course, you can make it very just pure theoretical physics and pure. Of course, you can do that, but I actually believe the power comes in this deeper union. So you can argue. So most importantly, S dot and T dot are deeply interactive, feeding each other in these cycles. So we have a whole lot of examples in the book on this, well beyond my earlier work with Tolu. Chapter 2 is about the intricate, another way your professors, those who are students in this room, say, what is the question, what is the answer? Or in engineering, you might call them problems and solutions. So you can either use questions and answers and problem solutions in a very analogous way. I just calling it questions and answers for simplicity. And finding answers, so there's a lot of fashion today that DARPA is really important because they were important in getting the internet going, of course, and some other GPS and so on. But Hellmeyer, who was actually from RCA Labs a long time ago, was a very famous program manager. He gave the dictum for DARPA. What are you trying to do? Articulate your objective using absolutely no jargon. How is it done today? And what are the limits of current practice? What is new in your approach? And why do you think it will succeed? Who cares if you are successful? What difference will it make? And so on. And that was basically the exam he gave before he funded somebody from DARPA. It's not bad. It's okay. But it is not asking all the new questions. Einstein, 50 years earlier, had said, this is the formation of a problem is often more essential than its solution. It may be merely a matter of mathematical or experimental skill. To raise new questions, new possibility to regard old questions from a new angle really requires imagination. And this is true for Einstein with general relativity and special relativity. It's true for Alexander Graham Bell, who said, I want to help my mother and my wife because they were both deaf. I want to convert electricity into sound or sound into electricity because they could cook with electricity. So who would imagine converting sound into electricity back in 1900 or 1878 or whenever? So those are the kind of questions, that's what I'm talking about. That question occurs both in engineering, technology, same with Edison. He always was asking questions. He said, I will be asking these questions. I can hire all the mathematicians and physicists I want. He had one arrogance, and the physicists had the other arrogance. We'll just hire all the engineers. And I'm against both of those views, you should know. So, but finding questions is also important. In fact, questions that are technoscience advanced in intricate dance of question answers. So Louis Pasteur was studying fermentation. He was working for a yeast company or one of those things for fermentation of making beer. And then he discovered what really became the laws of microbiology. Or my favorite subject, since I was the 5th director of that laboratory, the transistor physics laboratory, Bardeen, Bettner, and Shockley were looking for a majority carrier field effect device. It turned out they saw the transistor, but it was really minority carrier injection. An entirely different answer gave them the answer. So they were the smarts to recognize that there was a different answer. So you keep looking for that. That's what we mean by informed contrarians in our book. Then the more is different structure of questions and answers. I'm a great admirer of many of the theorists at Bell Labs. It starts with Bardeen, the two whom I'm old enough, folks. Both Phil Anderson died this past year. Bardeen died a few years ago. But Phil Anderson I knew really well because he was much contemporary of mine. And I'm an experimentalist, but I saw what a dynamo he was. He would walk into a lab if there was something interesting and be working with you. He was so dynamic. And Bardeen in his quiet way was the same. He actually sat there. So that was part of the culture. And Phil Anderson had many arguments with the high energy physicists. Because they said everything is in the fundamental particles. That's how everything happens. You've got God particle, whatever, and so on. And he says, no, I work in solid state physics and materials physics. And entirely new things happen which you cannot draw from the elementary particles physics. In fact, entirely new things happen, not just superconductivity, new phenomena emerge which require equal amounts of creativity. It's like saying biologists, when they observe, including exaptation, are not as smart as the physicists. And what gave that argument? So his point was, this is very important that there is no hierarchy in these disciplines. And to this, I would simply add engineering, of course. I can easily just add that, but I'm actually being honest with what Phil Anderson did. Because in fact, there was a lot of bias against material science and engineering. Because in fact, materials are so rich, they're just like looking at the stars. New things happen all the time and requires new imagination, new creativity, which I just can't start Q dot R squared or whatever and think you can actually do it. It requires real creativity. So that's the message, which the more is different question of answers. And the network structure of question and answers I already mentioned. You have even Einstein, his relativity was a very simple thing. But in there was hidden this equation E equal to mc squared. That led to nuclear fission. That led to the atom bomb and Fermi and everything else. So it became a very complex, that's why it became so important. That's why. And same thing with the laser. If Towns was really a technologist. He wanted to just invent and make something and see, can he do spectroscopy a little better? And then it completely revolutionized my life because fiber optic communication happened. So the punctuated equilibria. So consolidating and extending, so good science happens even while you're consolidating. Obviously you do this, and that is normal science. That's also I can call scientific development. So technology is not the only one which has development. Science has development too. It's the same language. I want to banish this difference between the two. It really is the technoscientific method. So the advances in mid-20s in deep learning were largely not algorithmic in nature. They were due to the cumulative advances in computational power and data associated with underlying technology. Some of you in computer science may challenge me, but I think this is my view, because in fact, after a certain stage, suddenly new things can happen. So because you suddenly had enough computational power or whatever, you know, all of two-dimensional physics was an orphan until metal oxide field limit transistors came, then you had an almost ideal two-dimensional system which you could study. And then, of course, in my group, people studied in gallium arsenide and got Nobel Prizes. And so the point really is they go in all kinds of ways. You have to be sensitive what there might be in science. You have to be sensitive what there might be in technology. So the industrial labs, like Bell Labs, like IBM, like Xerox PARC, like DuPont, knew that. They were aware of the science and they were aware of the technology and just didn't say it was the other. So not that what NSF does is wrong, but it's really important for DOE. They're missing half of the equation or some percentage of the equation. It's really important in changing the policy. China is doing it really well. So mark my words on that point. So in fact, technology advances cycles of surprise and consolidation. I just gave you some examples. So this is an example which is close and near and dear to my heart because this is what happened when I was director of solid state electronics research at Bell Labs. There was those of you who work in materials, there's a technique was invented by Alfred Cho, who was a member of staff of that laboratory, called molecular beam epitaxy. He's an electrical engineer. I call that electrical engineering. And they grew materials in new ways. And then Horst Stormer came, a member of my group, as a postdoc. I was only the department head, but he came to work with other scientists. So he could measure and he discovered modulation doping, which is also to make transistors. And so modulation doping. But he also wanted to understand the science, how the transistor worked. And he discovered the fractional quantum Hall effect eventually. And then I didn't say, you were hired to make the transistor, you're not going to do no, go ahead and do the fractional quantum Hall effect. That's what a great laboratory does. And others will do the transistor. So what I want to say is, you want to know the person, support the person, and be able to move from one to another when it is exciting to do. Too many program officers, including at DOE, the economists or some budgeteers funded you to do science because that became, or vice versa, and not do that. That's wrong. That's wrong. That's what Bell Labs didn't do. That's what, in the early days, IBM didn't do, General Electric didn't do, and that's why they won Nobel Prizes too. I mean, Ivor Gaber was a mechanical engineer who invented tunneling at General Electric. So it's not just Bell Labs. I'm just using Bell Labs because I know that. It's really important. And so the evolutionary science came, but now there's the normal science occurring. People are improving the fractional quantum Hall effect, people are improving the MBE, and suddenly something new may happen. That will be punctuated equilibrium. So this happens in both the technology space and both the science space. Don't ever separate them out. Let people go where you see. If that leader becomes important, must recognize and say, you accountants, this is important, this is what I'm going to do. That's what the Bell Labs managers were about, not managers, leaders. So research and development is unschedulable and schedulable. Research is the unscheduled quest for surprise and unexpected, whose outcome, that's why I said we'll table it discovery research. Technoscientific discovery research at the same time. So, but development is scheduled with consolidated extensive with a well-defined outcome because you're trying to see how well can I make this device? How well does the science work? It's a different mindset. It's important, but different. You will learn something new in that process too. So there is some research there too. So I will not spend much time. It is almost my time is up here. But research and development are both vital, but research is more fragile. I give examples of development because people confuse these things. Apollo, which President Kennedy, all my students whom I want to get, my goal is to get the social scientists, the artists, and the engineers talking to each other. That's what my undergraduate class, I've stopped teaching that. Now they're thinking of research, redoing it, finally realizing that this old man was not completely wrong. So they were trying to hire some young people because it takes 10, 20 years. For academia is more conservative than NSF or DOE. So Harvard is 50 years conservative, as Chuck West said when the school was inaugurated. I invited Chuck West, former president of MIT. He said Harvard takes a long time to do things, but it eventually will do the right thing. So, that's it. So I hope this will also happen the right thing. So Apollo was really an enormous engineering mission. It relied, of course, on various aspects of science as well, but really it was a technological mission, a huge technological mission. Moore's law really is a development mission, but tremendously important. And all kinds of things went to the semiconductor integrated circuits, I want to tell you. So that's different. But in the other side, in the research end, you have Bohr, you have Pasteur, Towns, And so there are different names you celebrate in this fashion. And there's science in the development side too. Why do people want to study silicon so much? Because silicon is such an important semiconductor. You want to know all its properties, because you never know what will happen. So these things feed on, so it's S dot and T dot. And T dot is the engineering method. S dot is the scientific. They are together, they're fusion. They have a lot of similarities. So research must be nurtured, not managed. We're coming to the end. You must align organization, funding, and governance for research. This is quite important, because otherwise, if the financiers are managing it, and you define the project very narrowly, you are stuck to do it that way. That is no longer research. Research is about the meta goal. So the Bell Labs researchers knew, or the DuPont, that you want to do something which may have long-term impact on communication. But in the process, you would be inventing new transistors, new lasers, all of them which turned out to be. And so the meta goal is there. So as you think of the meta goal of energy or so on, you should be thinking which are the ones which are going to change the world, and that's what should happen. And then there'll be proximate goals where you start, but as you start doing that work, if what you find you changes, because that's what the nature of research is, you should be allowed to change. You're made to you're judged later on. So if of course you're never successful, ultimately people have a way of finding out. We all know this person's creative. We know that. It happens. So the person becomes really important. And unless that's where a good dean is important, a good leader is important. They can screw you up. They can also make you happen, because they know that creative people are like children. They need to be nurtured. They will go off the beaten path. They're contrarians. They just won't listen to the conventional wisdom. They want to do something new and bang the table. I'm sure you have had some students that way. You listen to them, because in them, they might very well be a gem. So all of these features go, and this is what the reason my co-author wanted to do this, because I was giving a talk at Sandia, and when I left Bell Labs, I gave a speech at Bell Labs, which is recorded, nurturing the novel neocortex. AT&T was changing, and I wrote a piece which became quite a thing, and I'll show you that out of his history. But I think, so you got to really, all of the features become important. So NSF trying to do block funding of science and technology centers, that's a good thing. And then the managers have to be so organize it and change it after 5 or 10 years. If nothing happened, then you decide whether this should be modified. So those are important elements of how you do it. But the leadership is also really important. It's both the ground and the leader. And the mentoring, we talk about women and minorities. The real thing is science and engineering, technology are a social activity. That's why you're getting everybody together for this ERC. And unless we get to know each other, unless you rub shoulders with each other. And why do women and minorities complain? Because they're not part often the social milieu. The job of the mentor is to make them part of this equally as the others. And of course, then they must flourish just like everybody else. In fact, it's important for everybody. It's really important. So mentoring is often not understood properly. It really is important. It's particularly important for women and minorities, because right now they're not a large enough number. They don't have somebody to go to and pat them in the back and ask them and tell them. The Bell Labs leaders whispered many things in my ear when I was young. I did the same later on. I thought I was a great manager. I realized these guys 50 years before we were doing it. You just have to know it. People don't realize it, and how you do it very subtly. I don't give an order. I don't give Ali Shawkari an order. I find a way to make Ali Shawkari succeed. And then he will come back to me again, because he knows I'll give him the right food. So this is important. There's some very basic aspects here. So you must embrace a culture of holistic scientific exploration. And so we really do have to wake up many of our science departments as well. And engineering. Engineering also has an enormous amount of stovepiping between electrical engineering and mechanical engineering, and many of these disciplines are breaking down. So all of these go in. Computer science is to always argue they have to put science after computing. You should go to what do you call Frederick Brooks, who actually was a great computer scientist, a Turing Award winner. He said, scientists build in order to learn, engineers learn in order to build. And he always wondered why computer science has to call science after computing. So you could talk to Frederick Brooks, and he's a great computer scientist. I actually agree with him, because computing, for me, the greatest computer scientist for me was Shannon, because he really, went on his pogo stick. He always wanted to do something so-called applied, and then invented information theory, which is the basics. So I just want to mention this. So in found contrariness, Shannon was a contrarian. He really, but Bell Labs management did not prevent him from being in the, it's a big state Yankee company of this, but they had room for such a person. I had room for Horst Stormer. I feel very proud of that. Very unusual person. Or for that matter, Capasso. Capasso is a very unusual fellow. So that's important. And you must, nurturing doesn't mean you just give them a free run. There's always accountability. You all have to decide as a parent how you bring up your kids. But there's some balance there between nurturing them and then also pointing them in the right way. And so it is, and also it is more like a competitive sport. It's not just a free run. People, very often in development in Bell Labs, those guys, they're just playing there. No, that's not true. They're facing in a tremendously competitive environment, etc. You want to be, it's like a competitive sport. And of course, there still is performance review. Ultimately, with posterity, you judge the person, not immediately. So,
really have one question there.
Yeah.
How do you really account for evaluate the achievement? It's very subjective.
Beg pardon?
It's a very subjective matter.
Of course, you should. One thing, I have my own views about peer review. Peer review is important, but it's a conservative force. I'm actually very worried about academia and even the woke culture. I personally think I'm very socially quite progressive, but that doesn't mean you shouldn't listen to the other person. They may very well have points of view. And too often, even our students and our administrators melt, and we don't find people who might even give some different social point of view. They're not crazy people. I'm not talking about the extreme right or the extreme left. So this is really important that academia engages. And the same thing goes for science and others. So that's why the leadership is important. If the leader doesn't, and so on.
I agree with you 100%. We need to nurture young scientists.
Yeah.
But the last point, making accountable, and those are very difficult to do, in fact, because for promotion, you need to have a certain number of papers, funding, etc. That's not really, achievement can be more than just the numbers, right?
Of course. So, I have the whole lot of things. I'm trying to summarize in a view graph. One thing, the leaders in the companies which I worked in, Bell Labs and others, they were active in research. Much of their career.
But unfortunately, not whole university in the world of Bell Lab or anything, right?
Sorry, I was dean at Santa Barbara. I started a research department, a research program in a new area, and I had a very hard time getting funded. You've been vice president of Santa, you couldn't be doing the research. I did it because I worked Saturdays and Sundays. I did it at Harvard. So I just don't buy this. If you grow up with the right culture, I'm talking about cultures of extreme excellence. If Harvard and Purdue claim to be the great universities, they must have people like that. China has that kind of people. I see that in Kikan's way. That's why I asked him to write that letter for my book. So
my point is that it should be fair and...
So the leader, the president,
exactly, the leader.
Must be. So I'll give you an example. At Santa Barbara, which was, you was going to give the University of California credit. There was already Berkeley and UCLA. They were the two kings. Santa Barbara was a small community college in 1950. And slowly, population of California grew, all these universities created. Then Santa Barbara got a dynamic chancellor. He said, we got to change this, and we must build physics and engineering. So he managed to create an Institute of Theoretical Physics, got Shockley, Scalapino and others, and then hired Mehrabian, my predecessor, to build, and gave him 15 slots to build a new materials department. And then, so it is, you got to have the change. So I didn't go to Harvard without getting explicit commitment from the president of Harvard, because Harvard had a terrible reputation you talk about women and minorities. Junior faculty, be it white, black, or white, they never got their tenure. Right. It's different today. I told the president, I cannot build computer science, I cannot build engineering, I cannot even build physics unless I can bring young people. They are the future.
No,
And
I agree with 100%. All I'm saying is that to nurture the young scientists,
yeah.
we need to be more practical, but universities around the country and the world do not really nurture, they just count with their achievements.
No, sorry, I missed the whole point. The dean and the faculty have to say this is important. So I told the Harvard faculty that when the junior faculty are coming for the talks, we all have to be there. I'm going to lunch or dinner with them because we're going to hire the really good people. And you're going to be involved in that process and not just say, we're going to let them die. So you've got to change the culture. That's the whole point. The culture of universities needs to change. Sorry for getting excited. This is important.
That's my question.
Yeah.
How do we change the culture? Just saying it is the first step to do, but how do we change
All I can say, I had to change Harvard, which had never had this view of engineering. And so I'll give you some examples. EE was a pressure problem, and computer science was a pressure problem. I took extra trouble to go to computer science conferences and see how they are judged, including conferences and so on. And EE, we only had the theoretician. And in fact, the theoreticians were judged. Did they have a theorem? He said, what is the problem they solved? This is in engineering. They're not even mathematics. What theorem? I said, this is wrong. So I got Michael Rabin, was the most distinguished theoretical computer scientist, and my predecessor had just recruited H.T. Kung, systems from Carnegie Mellon. I said, we're going to chair that, and your task is to give me a program which makes computer science different at Harvard. And so on. So I got them together. So if the dean and the chancellor are not there, you're lost. That's why I said that from the beginning. Sorry for getting excited. I feel very deeply about this. This is important. And I'm talking about building a great institution. Bell Labs was a great institution. Harvard is a great, and Beijing, quantum, Tsinghua is a great institution. I mean, that's what I'm talking about. That's what the future of the United States is. President Kennedy was a leader because he said, we want to go to the moon. People say, why are you wasting money going to the moon? He said, we want to do something which is hard. It defines us as a people. So the point is, a chain is as strong as the weakest link. You've got to build that system. So I'll give you an example. This gets very personal. I'm being recorded. I was very cognizant of the power of the faculty. I got some of the best faculty on my side. Michael Rabin and H.T. Kung. In mechanics, I got John Hutchinson and Jim Rice. They're some of the most cited authors in engineering. They realized what I was saying. They backed me, and they converted all the flunkies. Second, the EE was really hard. I never chaired a committee myself. But I said, you cannot, the physics was all dominant. So we're always doing condensed matter physics, which is my field. But I knew it is too limiting without all the devices. I was used to having Horst Tormer and Federico Capasso. So I told the president, I'm going to chair one committee to bring a top-notch person who is better known in physics than most people in the physics department, and he's going to be only professor of engineering. That was Capasso. That changed the chemistry. Then young people started coming. So it has to be a combination. If the leadership is missing and the others aren't, and then there were others in physics writing to the president, Venkatesh being his friends, but the president knew what I was doing. It was the right thing to do. So what I'm saying, if you don't get a good dean or good president, you're sunk. So I'm lost.
That's what I'm saying.
Yes.
How do we implement the nurturing if we don't have a good...
No. You implement literature, the people who are in it, they tell you. So Harvard is now actually have mentoring. I became double dean because I saw how this was working. So now junior faculty all over. It's not just about women and minorities. The system has to change. It takes time. Right. Of course. So mentoring is really important. Yes. And I never want to be hired because I was hired because I'm an Indian or something. I want to be hired because you're good. This is true for every woman. It's true for every black. It's true. I believe that. But they do need that environment to succeed. And that is the responsibility of the leadership and the faculty. And you have to care for them just like you care for your students. If you don't, there's some people who are not good with their students and postdocs. They abuse them. I'll tell you, Santa Barbara had a culture that we allowed people to work together. I have papers with Herb Kromer at Harvard, not every faculty, but George Whiteside is very open. I have 3 papers with George Whiteside. I never told my students, you can't go and work with that professor because I said it's going to be good for you. You'll have 2 professors writing for you, not just one. So all kinds of cultural issues are there, and
Your
so.
talk was so inspiring. That's why I'm.
No, it's important. So I don't know. I get very frustrated because people don't understand the human aspect here.
Yeah.
The human aspect is so important, which is so critical. It really is. And that's what Bell Labs was about. That's why I put that nurturing purposely. And it's really, at the same time, it's care and accountability. I knew that Horst Dormer was smart. I knew that Federico Capazzo was smart, and they knew that I knew it. They knew, because I supported them. I made it work. When the bureaucrats came, I said, leave them alone. So it happened because of people interfering with me. President Summers and Rudenstein told them, Venki knows what he is doing, leave him alone. Because they knew I was competent. So if your boss doesn't have the confidence, the dean doesn't have the confidence, then of course you have a problem. So this is true for all organizations. But the nurturing is very important. It's an important characteristic. It's very subtle. Because good people want to do things. Your own children want to break away. Sorry for getting excited. This is essentially, so I have this picture because I was giving this opening talk. This is the second time I'm giving a talk in the book. This book just got published. It was at Sandia. And when I went to Sandia, I took a picture of mine before, and Bell Labs News had an article on me. I was going from Bell Labs just to run Sandia in those days. And that's Alexander Graham Bell. And that statue says, go off the beaten path, delve into the woods, you'll find something which you've never seen before. That was always my calling card. There was a vision. So your dean and your president must articulate a vision. The faculty have to buy into it. Not everybody will, but you get the leaders. I was fortunate that Michael Rabin and H.T. Kung and John Hutchinson and Jim Rice, some of the biggest leaders, members of the academy, came on my side. Of course, I worked hard. I got their confidence. They realized that I was not a fool. So of course, you had to have, it's a mutual thing. So I took every young person I recruited there, because this is what Bell Labs is about. I'm going to give you money and support, but the idea is to look for new things and to change how the things work. And not everybody succeeded, but a fair number. That was the vision. And that is what I wrote an article on nurturing. It was published in Bell Labs News, and he wanted me that. So now it's become part of the history, just like Ralph Bowen, what it takes that here. Because I did never like the word manager. Harvard Business School is a great business school for running big companies. That's different from running an academic institution or a research organization. That doesn't mean the bad companies are bad at Harvard. It is different. I'm talking about something very special. I'm talking building very special institutions for science and technology and really doing it right. I'm passionate about it at my old age, even though I'm 82 years old. So that sort of ends my talk. I think in a sense, we should, half an hour is reserved for questions, so we should actually have those questions. But I think the future of Bell Labs 3. So Bell Labs 1.0 will go, so to speak, from Bardeen Breton to Stormer, Sui, and who discovered the fact, I'm just the time period which I know of. It relates very closely. And Bell Labs 2.0 is really what is beginning to happen now in various ways. Santa Barbara is partly Bell Labs 2.0. They like to say that Bell Labs was Santa Barbara West. That's what Jim Merz would say. But anyway, but now, because Santa Barbara was very lucky, Moravian had all Bell Labs was closing down, IBM was decreasing its research, Xerox and ExxonMobil, all of them went there. And we all grew up with the culture of what is the most exciting problem to solve. Is it physics or engineering? Physics and engineering all together. And there are a whole bunch of other things. Our chemistry department in Santa Barbara, I'm sorry for looking at you because it's important, is very money conscious. And who has the FTE? Yeah. So we had, many of you might know the name Tony Cheetham. He was a well-known professor of materials in organic chemistry and organic materials. And he obviously needed chemistry graduate students. But his appointment was Department of Materials. He had just joined 6 months before me. He said, Venki, I have a real problem. I can't recruit chemistry graduate students. So I went and spoke to the provost of Letters and Science. But chemistry faculty were not for it. Physics was much more open. Physics we had very good try. So I said, look, Tony Cheetham is a very distinguished faculty member. Santa Barbara has a quarter system. I will transfer a quarter of his FTE and his salary to the chemistry department. He will teach quarter time in chemistry. Then he should have the privileges of the chemistry faculty member. You are not costing you a dime. And he's a distinguished faculty member. That broke the ice. I said, we'll have only one agreement. I don't want to stuck future deans. When Tony Cheatham, if he retires or leaves, then that FD returns back to engineering. And that then future chemists began to reverse the thing. So somebody has to be there who's broad-minded and who will change. And hopefully there are faculty members here who will push their dean and their vice president of research in those matters. And I'm not a revolutionary. I'm somebody who cares about the future. So this is important. I'm giving you real examples. I hate to do it personally. I'm being recorded. It is very sensitive what I'm talking about. So the future, of course, here we have Google and with DeepMind and UCSB and Janelia Farm and even Harvard. And funding becomes very important. Harvard's funding becomes obviously very critical. We're all dependent on it. And the future will be what I think what some of you are talking about. In fact, I have worries about AI. Because in fact, it's like the way they do it. You can imitate a dog, but you go from dog to cat, it becomes a problem. And then we know all these other features in there. And the human brain has been perfect over so many years. If I were younger, that's the field I'd want to reform. It's a long ways before it becomes, it's very important, extremely important. Everybody will go headlong with going to have automobiles made with AI until the first accident occurs. Because in fact, it's amazing. I don't know how many of you have driven in the chaotic streets of Mumbai or Calcutta. Believe me, people go opposite direction. I no longer sit in the front of the car. The taxi driver never has an accident. But no AI system could ever take care of that. It's something about, so this is my example. It's going to take it's really true. I'm not joking. I'm frightened to sit in the front seat of a car in a crowded city in India. And believe me, I've been to Nigeria. Lagos is worse. So there are places which are worse than even Bombay and other. And I don't know how good Tehran is, but probably slightly better. So AI has a way, but AI is going to be important. I actually think ultimately there'll be some hybrid, and how we actually work. So actually thinking about these complex systems. And in fact, one of the really important things, computer science has to merge much more with statistics and with engineering. Machine learning will never become important unless the software and the hardware merge. So don't forget the hardware. I'm very worried. We're now creating a center for computational AI at Harvard with a big amount of money. Zuckerberg has given $500 million, but there does need to be the hardware component as well. I very strongly feel computer sciences with computer engineering, much more, and then with the larger society, with the society. So these are things which I'm worried about, and at least that's what I would do if I were still dean. So I have gone way in my excitement. Ali, I don't know if that's what you bargained for, but I think it's time to say thank you. And there are a whole bunch of selected readings which we have, but I'm not going to become rich by selling this book. This is a scholarly book, but hopefully some of you will find it useful.
Thank you. We have time for questions.
Amongst the folks who credited for reading the first draft of the manuscript and so forth, one of the names stood out for me personally because Ambuj Sagar was an old friend at the University of Michigan who then went to Harvard, and now he's at IIT Delhi. Is it the same person?
It's the same person. So this is a story. Ambuj Sagar was a PhD in polymer materials from Michigan.
Correct.
Then he decided he wanted to be more in the public policy arena, and he postdoced with John Holdren at Harvard. And he also went to Michigan and other places because he wanted to learn that area. I made it a point. Sheila Jasnoff is a collaborator of mine. She's a great STS scholar, but she believes in the purity of STS. I don't believe in that. I actually believe you must understand STS, you must also understand the other side. It's like I must understand science and I must also understand engineering. That's what Bell Labs taught me. That's what my thesis advisor taught me. Work with the materials. He was a low temperature physicist. That was a lesson. So Ambuj Sagar, then I recruited him to the School of Engineering, and he was still working with John Holdren as an assistant dean to help me with strategic planning. And I wanted to have a signature concentration at Harvard School of Engineering called Technology and Society. So because I wanted somebody who understood materials and also had gotten that. So he helped me a lot, and that got him School of Public Policy at IIT Delhi. I had to convince the director that many times that he's not a fool, he's not just an engineer, but in fact you want him. But I feel I care deeply about the United States, and then next, I still love India, because I was born there, and I feel very worried that it's the biggest country, they're not quite up there. So the IITs need to change, it's a different matter, but it's the same Amrit Saga. So he, Laura Anna Donald, and Sheila Jasnoff, I credit a lot, because Tolu Odomosu was Sheila Jasnoff. So I made an effort, and I told Sheila, we're going to have postdocs, they're going to have both an STS degree in engineering or science degree. I don't mind any field of science, could be computer science, but it's a way of thinking along with the other. I just don't want a pure STS person. They must understand both sides. So Tolu Odomosu, who did the first book with me, he's had a master's in electrical engineering and a PhD in science, technology, and society. So he understood how transistors worked. He could not otherwise analyze it. Otherwise, I have to do everything myself. I can do it simply because I have 50 years of experience, but they don't have 50 years of experience. Am I being clear?
Yeah,
so it's really important. So there are people who should know engineering hardcore. That must be there. That should be still the main mission of Purdue. But they still have to be broad people, and some people have to be trained to learn in these other areas. It's very important for the future of technology, for the future of physics and engineering and the society. I have too many people at the Kennedy School who think because the power comes from the socket, it's clean. They don't realize all kinds of fuels are being burnt and everything else. That's the impression people have. It's a black box. Every one of my students know how student knows how a computer works. And believe me, I'm not a computer scientist. They all know what do you call a communication and how that works and how it's different from a computer network and the transmission internet protocol. All of them, these are non-engineering majors. So I had to learn all of that myself to teach them that, and I had a TF who had some feeling in computer science. So it's not easy. We don't train people like that. So now finally they're going to create a program. So I used to teach this class by hiring very unique postdocs, some of whom were listed there, to work with me, because I couldn't find anybody else to teach these. Either they knew physics or they knew only social science. It's really difficult. It's really tough. We're too stovepiped. And Harvard should not be training those kind of students. That doesn't mean the specialists are bad. But I'm talking about a different thing. Society. Sorry.
So this is a very thought-provoking talk.
Yeah.
One question I have about Bell Labs, that you have said many positive aspects of the Bell Labs ecosystem as a model. But I also remember that, not I personally, but I also know that in order to do silicon transistor, they had to leave Bell Labs and do it in Texas Instruments. The people left Bell Labs, and also for the integrated circuit, they could have done it at Bell Labs. They didn't. I wonder why certain things happen like the original invention of transistor, fractional quantum Hall effects. But other things are they have to find expression somewhere else.
So there should be no ambiguity. I'm glad you brought that up. Remember, I had that view graph. Transistor was important, but so was Moore and the integrated circuit. Okay? And so Bell Labs was also used for they had such power, they were trying to integrate millions of germanium transistors on a chip until Kilby and, of course, it was a very simple idea, but Kilby and Noyce had, why don't we just evaporate and make them in a thing? And it happened elsewhere. It happens all the time. Bell Labs dissuaded Towns after he invented the laser because they didn't see immediately an application of communication. And he was unhappy. So they do make mistakes. I never wanted to, of course, this is true. And Harvard makes mistakes. MIT also makes mistakes. So I think one has to be aware of that, of course. So there should be no ambiguity on that point. So in fact, sometimes they have to flower elsewhere, or exapting will happen. And in fact, the person who did the fibers was Charles Cow at British Telecom, who realized that you could actually transmit through fibers because they're full of OH and everything else. They could hardly transmit a few millimeters. And now you transmit 200 kilometers or 2 miles, right? So I think it's not, I always was also careful. It also involved Bell, IBM, involved Xerox, all of them. So in fact, that is, of course. But there's a cultural thing though, which is quite common in all of them.
You're saying that a vibrant ecosystem like this will produce more positive results than negative. There'll be both positive and negative?
Yeah, of course. But I believe that the combination will be in general somewhat better. Yeah, right. Because it's just the broader. Right. You're narrowing. I'm against the stovepiping. I'm really for the broadening. Yes.
So very interesting talk.
Yeah.
We could discuss it for a long time. So I guess my question is, I think from an engineering audience, you would generally get a receptive view that, yeah, this all makes a great deal of sense. Many engineering faculty publish in the scientific literature, maybe mostly in the scientific
Yeah.
literature. It seems like the resistance would come from the science side.
Yeah.
So my question is, how do we change? I could see it can be ground up, which means we need to get you to go and give seminars like this to the physics department and the chemistry department
Yeah.
and the biology
Yeah.
department. Or it needs to be top down like you did it, and you need to appoint a leader. And
So it is both. So I think, first of all, I do want to, for me, that my physics colleagues don't think me to be crazy is important. And you should know, I've shared with many of my physics colleagues, I've talked about David Nelson, Bert Halperin, very distinguished theoreticians, etc. Because I mean, Phil Anderson is one of the most, and so on. And for me, the biggest compliment was they loaded me so much. For a while, I was Dean of Physical Sciences as well, and managing math department and all of the others, etc. And they're great, 3 field winners. So I think Harvard has come a long ways. And biology, interfering biology, Santa Barbara, I think many universities are changing. And so I think I was for a long time, I'm still on the membership of the American Academy of Arts and Sciences. And the secretary of the Academy, she has now become Undersecretary for Energy. Her name will Geraldine Richmond. She says, Venki, you engineers are always much more open than my own chemists and physicists. And I think there is an issue of the culture, but Bell Labs, the materials culture is very good. They really are materials. Is it chemistry? Is it physics? Is it engineering? It's all of them combined. So I think that's the difference between the materials kind of people. And so one has to build on that. And changing culture is a long, hard process. It is long, hard. And you're correct. The bigger problem is with the science end. Yes.
And you could do it in seven.
That is why I bought a best Capasso in, and I was a physicist. And so now my current successor, he's a chemical engineer, he's having greater difficulty because it's still hard to accept because he doesn't quite understand. So that's why you got to know both areas. Luckily, I had credentials in physics. All my early work and my later credentials are all in engineering, but that's okay. So this is why to break the divide, you need credentials in two. It's very hard. It's not easy. So I do not want to. So the president of Harvard, the story was that all the previous deans had been famous theoretical physicists: Paul Martin, Harvey Brooks, John Van Vleck, my predecessors. I was the first non-Harvard PhD and experimental physicist because Gates studied at Harvard, left in his junior year, and of course became very rich by the 1990s. And the president of Harvard went to Gates and Balmer for money. They said, we'll give you money as long as you find a dean from the outside who understands technology and engineering and computer science. And then we'll give you a building for computer science and electrical engineering. So Gates and Balmer gave money, and the president sent the dean of the faculty all over the country. I didn't know that. Suddenly this man comes to talk to me. Another dean comes to talk to me. I was not looking for any job. And he got fascinated. He had me meet the president, and it happened. That's how Harvard does it. So, but anyway, so there had to be some forcing function which has to be there. And some of it comes from the faculty too. So Santa Barbara had a Herb Kromer, who was actually kind of a dynamo. Some of you probably know Herb Kromer. And then he needed a companion with Jim Merz, who was more, you had the less people skills to combine, So that's what I did. I used some of the most distinguished faculty, like Michael Rabin and H.T. Kang. And then I got Capasso, who had impeccable standing throughout the. So that's what has to be done. I'm talking about building really great institutions, which is important. Purdue is a great institution. So this is not easy. I do not want to make, or even the Bell Labs thing is not easy. But generally, and of course, mistakes occur. Harvard has made lots of mistakes, including not having engineering for a long time, after having started computer science and everything else. Yes.
Were you at Santa Barbara at the time of Chancellor Henry Yang?
Yes. I was telling somebody, I've been there already about 2-3 years, and I got a call. And of course, Chancellor Yuling got into trouble with the faculty, so she was leaving. And then I got a call from the office of the president, will you make an appointment for Henry Yang in the Department of Mechanical Engineering? So I knew who was going to be as a chancellor. So I actually made his appointment, including giving him a good academic salary. Of course, it was, it was a pro forma thing. I knew it had to be done. I had to talk to the faculty, do the case, and really do. I did it properly, but I had to do the work.
The dean at
yeah, right. So I know him very well, and he's still there. He's the longest serving chancellor, period. I still interact with him.
Any questions? I have a follow-up question from what Kinam asked.
Very important. I'm getting excited, but you're right on. I'm not disagreeing with you.
About this evaluation. So actually, a very practical question. This idea that some of these things become subjective, otherwise you're counting. How did you do evaluation at the labs? What was the things you were looking? You were asking?
First of all, let's say there's I was a member of the physics division. Physics division had 3 laboratories. Physical research, typically 50 members of PhDs in each lab and equal number of technicians. So each person was 100 people, say. Physics division, I started in that physics laboratory, chemical physics laboratory, and third was solid state electrolysis laboratory, which is really the transistor physics laboratory. And so I started the physics laboratory. So the executive director would be in charge of all those. He's like a super dean. He would get together with the directors. The directors, in turn, will get together with all the department managers and have a discussion of all the members of staff. And sometimes, let's say you're in EE and you're in materials. The materials chair would be supporting you more than them. So there was in a sense, a peer review or something that was done by a group, and then you still had to justify one other level and so on. And the people wrote an annual report. This is what they did, and the papers they were giving. The really good ones short off. The really good and those who you knew. In between, you can argue a lot. It was definitely not perfect at the in-between level, but that's okay. They were all solid people. But the extremes you knew. Because these were all very intelligent leaders who also were active. We always went to conferences. You wanted to know what's going on in the world. You can't have a leader sitting in their office up there. You've got to be part of where the work is done. I went to so many computer science conferences. It's not my field, but I had to get to know. And when I first went to Harvard, I'd get letters for junior faculty. They would write me nasty letters. Your predecessor didn't hire so-and-so. Why should we recommend anybody? I never got some letters in Santa Barbara. I got them at Harvard. Then, 5 years later, I got a very different set of letters because they realized we were doing it right. So this is really very, very important because I got to know them and I made a conscious effort to hire that. I'm sorry, I don't want to pat myself in the back. These are, people did it. Ralph Bone did it. Go read his book. I was surprised. I was humbled. I was just one of the children of those people. It becomes a cultural thing. The culture, I'm worried about academic culture becoming too woke. In this whole issue which are happening. We talk about Republicans and Democrats, but we really do have to be open because there are many, even with vaccinations and so on, we cannot do it by fiat in some fashion. This is a very sensitive subject. I'm no social scientist, but I'm a fairly good people person, I think. And somehow we must be open to different points of view. I worry that academia isn't, and very often departments aren't either. They want everyone to be just like them. Partly an issue even for Bell Labs to really recognize, but Bell Labs had a way of recognizing the contrary person because they were looking for that contrarian. But that made mistakes too. Some people were really very destructive. Yeah.
Maybe the last question.
Yeah.
Do you have any advice on how to nurture creativity?
Do you have what?
Nurture creativity. How to nurture or like
Huh?
how to nurture new faculty into creativity.
Yeah.
Do you have any advice on that?
Any advice?
Yeah.
Yes. So first of all, you really have to treat that person really in a way, here's what I would do. First of all, I'd get to know them when they came for an interview, even though I wanted to convey to my senior faculty this is important. Because what the hiring process is one of the most important processes. So I always made it a point not only to go to their talk, even though I'm not an expert, obviously my expertise in nanoscience and parts of EE and device physics and applied physics, but I would go because you get a feeling, and I would always go for lunch or dinner with them to get to know the person. And second, I would meet periodically with them. I tried to make connections for them and give them we have very good feedback system. At the end of 1 year, I would meet with them personally. First of all, I'd be walking, going to their offices. They'd be not afraid that the dean is coming, just to chat with them, how they are doing. People tell you the truth, not in a formal place, but when you naturally meet. So I don't know how to teach people this. When Larry Summers wanted to make a big engineering school, I said, no, I want to limit the total size because I want to be in touch with the faculty and the students. When students would come to Harvard and MIT, there's a lot of competition in Harvard and MIT. I would tell the students, MIT is 10 times Harvard size. They are a fantastic engineering school. But try and go and meet with the dean. See if you can meet the assistant to the assistant dean. If you want to come to Harvard, you'll get to meet me. Because we are not that large. So you've got to decide, you have to make a decision here of how you'll, but the culture has been, even in a big school, where then the department heads and all have to be really cognizant of the younger faculty, that their success is my success. That's what that article in Novel Neocortex was. When the people succeed, then I succeed. So it's a cultural thing. So you really have to get to know the person. So junior faculty are comfortable with the person, and they will tell you what the issue is. And I would have a formal review with the faculty in the second year, and then I would meet personally with the young faculty, and they would get 3 kinds of responses. Just keep doing exactly as you're doing, or you do need to improve in certain areas, or if there are troubles down the road, they got to know early so they can make their careers change. So all of this is important. That's all part of mentoring and feedback. So it's very complicated, it's a very human thing. So somebody has to keep on interviewing me, and then you have to tell them, because that's why AI is so difficult. It's a human thing. So I'm glad you asked, but I hope is there a mentoring program in Purdue School of Engineering? It's very common now at Harvard.
We have mentoring for new faculty.
Huh?
There are some, yes.
But serious, but people really take it seriously. Go for lunch or dinner with them and take them and make sure they succeed. Actually, Peter Kakatowicz used to be that with many of the control faculty. He used to bring them, make sure I got to know them, etc. And so the senior faculty has a very important responsibility there in mentoring. In fact, there are some good examples even at Santa Barbara of people who helped me with that, because obviously you have limited time. And so the dean who chooses the mentors must choose people who are that kind. Some people are loners, you've got to leave them alone. I'm not saying my formula belongs to everybody, but the job of the dean is to identify those who will actually be good mentors. Because they care. Most of you are in the university because you care about teaching and students and all those other features. If you don't, you shouldn't be there. You shouldn't be here. I'm sorry, I get excited, but this is true.
Let's thank Venkatesh for